Well, let us see the first problem. The first problem is written here. We need to estimate the pressure in a tank of 1 meter cube filled with 100 kg methane when left in the surroundings. Temperature is 40 degrees centigrade. What are the data which are given to you? The data of Tc, Pc and omega are given to you. What is the gas? It is methane. You know the molar mass of methane. What is the molar mass of methane? It is very, you can always find it out. This is equals to 16 into 10 to the power minus 3 kg per mole, right. Tc, Pc and Vc are given. So, quantity of methane in the gas, I will put it CH4, this is equal to 100 by 16 into 10 to the power minus 3, which is 6.25 kilomoles, you know it, fine. What is the molar volume of methane? VCH4, this will be equal to 1 pi 6.25 into 10 to the power 3, fine. This is nothing but equal to 1.6 into 10 to the power minus 4 meter cube per mole. What is Tr in this particular case? The temperature is given as 313.15 Kelvin by 190.7 Kelvin, which is 1.642. What is, so therefore, you know Tr, and what is Z equals to? That is equals to PV by RT. Your P is given, V is given, V you have already found out, this is the V, the P is already given, it is P is not given, sorry, R is given, T is given at 40 degrees centigrade. So, if you substitute all these terms, what do you get? You get 46.41 into 10 to the power 5 PR into 1.6 into 10 to the power minus 4 divided by 8.314 into 313.15. You get Z as 0.2852 PR, right. So, see one thing, what are the data you have at hand? With the data you have at hand, you are supposed to find out pressure, agreed. You know Tr, you can find out Z as a function of PR, agreed. But in, and you also have a compressibility factor chart which gives you Z as a function of PR for particular Tr. So, in this particular case, if you have a Tr of 1.642, so in your particular condition will lie at any particular point on this particular isotherm, agreed. But where it is going to lie, you do not know it, you just know it is going to lie on this particular isotherm. You need a trial and error method to find out exactly where it lies. It is a very difficult thing to do. Without anything, you cannot do a trial and error method. But at the same time, you know something else. You know that Z has a linear relationship with PR as well, with the slope of 0.2852. So, what do? The best way is to do is you draw a straight line from the origin with Z equals to 2.582 PR, and you see where it intersects with the isotherm at Tr equals to 1.642. So, naturally, this is going to be the point in question, and for that particular point in question, you know what is Z0. You find that the Z0 is nothing but 0.87. So, naturally, from here you know that at Tr equals to 1.642, what is your PR going to be? Your PR is going to be Z by 0.2852. So, you know the PR is going to be 3.05, right. So, you know PR, you know Tr, and for better accuracy you would like to refer to the Z1 versus PR Tr chart. From the Z1 versus PR Tr chart, if you, since you know PR and Tr, you can find out Z1. The Z1 you will be finding out, just check it up, this is the data I am giving you, this is nothing but equals to 0.23. Once you know Z1, you know Z, then what is the next thing? You can, this is basically Z0. You can find Z as Z0 plus omega Z1, omega is already given. So, from there you can find out the final Z. Using this final particular Z, you can find out PR as Z by 0.2852. You get PR as equal to 3.06, and from there you can find out P. And this particular iteration, possibly it has to be done a number of times. So, from here you get a particular Z. Again you start from this particular with Z0 equals to 0.86, Z1 equals to 0.23, PR equals to 3.06, TR equals to 1.602. You get a PR as 3.024, right. with this particular PR as 0.324, there are several iterations maybe which you have to do. Finally, you get your Z as your Z0 as 0.86, Z1 equals to 0.23, PR at PR equals to 3.204, TR equals to 1.642, from where you get your final PR as 3.024. When the calculations converge, from where you get your P as 140.34 bar. So, this was the first problem. Let us go to the second problem. It is a pretty straightforward problem. You have a cylinder of 0.1 meter cube. So, your volume is 0.1 meter cube. The pressure is also given, it is 8.25 megapascal. The temperature is given as 25 degree centigrade. You are required to find out the mass of ethylene, and you are supposed to do it by the van der Waals equation of state, 2 and 3 parameter compressibility factor chart. Right. So, for the van der Waals equation, A is given, B is given, but it has to be a trial and error technique. You need to find out, see, you know the total volume. If you can find out the molar volume, then you can find out the mass of the mass of ethylene inside this. In order to find out the molar volume, you need to write down the van der Waals equation in the cubic form. Once you write it down in the cubic form, you need to solve it iteratively. Now, remember one thing, when you have to do a iterative calculation, first guess which you should be using is the value of V obtained from the ideal gas state, right. So, therefore, that will be your first guess value for solving this particular cubic form of equation. So, therefore, from the initial guess value you get V equals to 1.196 into 10 to the power minus 4 meter cube per mole. This initial value, the initial value has been obtained from the ideal gas equation. Once you know the molar volume, so then from that you can find out the quantity of ethylene as the total volume divided by the molar volume. This has been obtained by solving the cubic equation of state. The first guess value for the cubic equation of state was from the ideal gas value. So, therefore, from here you get that the total moles of ethylene in the cylinder was this, and the total mass of ethylene was 23.411 kg, provided ethylene obeys the van der Waals equation of state. As far as finding it out from the 2 and 3 parameter compressibility correlations, what you need to do, you need to find out TR. Find out TR, it will be equal to this. Find out PR, this is going to be 1.6123. Since you know TR, PR, in this case there is no need of any particular trial and error. You can very well find out Z0 from the graphs which I have given. You can also find out Z1, the graph is also provided here. Once you know these two, you can find out Z, omega is also given, I believe. So, you can find Z as Z0 plus omega Z1, substitute these two and the omega is 0.089. From there you get Z. Once you get Z, you can find out V from this particular equation. The V from the 2 parameter law, it comes out as this, the molar volume 9.765 into 10 to the power minus 5 meter cube per mole, from where you get the mass of ethylene, it is obtained as 28.67 kgs, and from this is from the 2 parameter law. Similarly, if you proceed with the 3 parameter law, you get the mass to be 28.48 kgs. It is worth noting that there is quite an amount of difference between the van der Waals prediction and the 2 and 3 parameter law of corresponding states. Naturally, this particular deviation it occurs due considering the approximate nature of the van der Waals equation as well as the inaccuracies inherent in the 2 and 3 parameter law of corresponding states. It is also important to note that the predictions from 2 and 3 parameter models, they do not vary much, which automatically implies that we can safely use the 2 parameter law of corresponding states, provided we are not very near the critical conditions and not very near the saturation curves. Now, let us go to the third problem, a slightly different problem. What do we have here? This is a problem on the virial equation. What do we have here? We have methyl chloride at 100 degree centigrade. The first two coefficients are provided and we would like to find out the work required for reversible isothermal compression of 1 mole of this methyl chloride from say 1 bar to 55 bar at 100 degree centigrade, and you are required to work it out both in terms of the Berlin form of equation and the Leiden form of equation, or in other words from the volume explicit form and as well as the pressure explicit form. This is a pretty simple problem. You have got B1 V, you have got B2 V, you have got T, you have got P1, you have got P2, right. From here again you start with a V initial value. Remember one thing, V initial value will be nothing but RT by P1. From there you are required to find out V final. What is W equals to minus of integral P dV. You know PV by RT is nothing but 1 plus B by V plus C by V square, agreed. So, we can easily substitute this in terms of P. In terms of P, this equation becomes RT into 1 plus B by V plus C by V square into 1 by V, right. So, therefore, we are going to substitute it here, we are going to get this as RT integral V1 to V2 dV by V plus B dV by V square plus C dV by V cube into this equation, from where we get the work done as 12.62 kilojoules per mole, right, when we are using this particular equation, fine. Now, suppose we use the other equation, then in that case we need to find out B prime and we need to find out C prime. We know the equations, it is B by RT. In this particular case also we know the equation, it is C minus B square by RT whole square. We can find these two values. This value is going to be minus 7.817 into 10 to the power minus 31 by bar. This is going to be minus 3.492 into 10 to the power minus 5 1 by bar square. Once this B prime and C prime are found, the rest is pretty simple. We know PV by RT equals to 1 plus B prime P plus C prime P square. We know what is V equals to, again we can substitute it in terms of RT by P, 1 plus B prime P plus C prime P square, fine, or else we can write, we can just expand and write it down. So, therefore, from this particular equation we know what is dV dP equals to, it is equals to RT into 1 by P square plus C prime, fine, and we know what is W, this is equals to RT integral P1 to P2 minus 1 by P plus C prime P into dP, which gives you the value of 12.596 kilojoules per mole. So, therefore, this is one particular way that we can do it. There is just one thing which I would like to point out. If you observe the work done which you have obtained by using the same equation in two particular forms, in one case you get the result as 12.62, in the other case you get the result as 12.596. They are not completely identical. This suggests this happened why? Just because we had taken the virial equation truncated after the third term. This shows that if you would have taken additional terms, the predictions would have been better in this particular case, right. So, in this particular way you can try several other equations or several other problems. There are a lot of problems which are available in a large number of textbooks. You can try this out. You can try problems involving cubic equations of state, virial equations of states, and we will also be providing assignments to you for the same. Now, before I end, there is one more problem also which I would like to do. It is not exactly on the PVT behavior of the gases, but on phase equilibrium that you have already covered. What is the problem? A very interesting problem. It tells you about the transition from the vitreous to the grey form of selenium, right. What does it tell you? It tells you that suppose we have selenium in the vitreous state, we would like to convert it to selenium in the grey state. It is given that you are supposed to find out delta G for this at 25 degree centigrade, fine, and What is the data given to you for finding this out? The data given to you is that at 125 degrees centigrade, they are at equilibrium. What does it mean? It means that at 125 degrees centigrade, delta G equals to 0. Fine. Using this data, you are supposed to find out this. How to do this? We want to go from this state to this state. Remember, here it has say some particular value, say some say G SE, here it has got something say G SE gray, and here it has G SE V, suppose, right. From here to here we wish to go. We can devise any path for it. So, what do? I instead of this path, I devise a path this, then this, then this. In this path, what are the things that I know? Here the change is delta G1, here the change is delta G2, and this here in this case the change is delta G equals to 0. So, therefore, can I write delta G at 25, it is equal to delta G1 plus delta G at 125 plus delta G2. Delta G1 is the Gibbs free energy change of selenium vitreous when it goes from 25 to 125 degrees centigrade, and delta G2 is the change in the Gibbs free energy when the gray selenium goes from 125 to 25 degrees centigrade, right. Now, if I can find out delta G1, I can find out delta G2, I can find out the delta G transition at 25 degrees centigrade. What are the data I have for finding these two out? The data which I have is the entropy of transitions data, right. So, from the entropy of transition data, what do I know? I know delta G1, this is equals to minus S dt from 25 to 125. This is for the vitreous case, and since it occurs under a constant pressure. So, therefore, this is just entropy change which happens, and this is this delta G is going to delta G 25, this is 125 to 25 again minus S the gray variety dt. You know the changes in dt, you know SV Sg which is independent of temperature. So, from here if you substitute the values, what do you get? You get this is nothing but minus 7.4 125 just I am substituting the values, minus 10.04 25 minus 125, which gives you the value as 264 calories. For this transition, delta G is positive, which automatically states that this transition from vitreous selenium to gray variety of selenium, it cannot be a spontaneous process, but the reverse case has to be spontaneous process. So, therefore, it is obvious that at 25 degrees centigrade, the vitreous form is going to be much more stable, and the reverse reaction is going to be the spontaneous reaction, and at 125 degrees centigrade, either of these states can be stable, and if we know the condition at one particular state, we can find out the condition at the other state. So, this completes, or rather I had tried to do a few tutorials on PVT behavior to give you a better feel, and since I had some time, I thought I would just show you the importance of phase equilibrium conditions to find out any particular transition or any particular state from some known particular state at some other conditions. We will be continuing our discussions regarding the estimation of properties, and then we will be going for mixtures from the next class onwards. Have a good day.